Okay, so in this question, we are talking about the central difference scheme for approximating the second derivative of a function f. And when you try to approximate the second derivative of function f by central difference scheme, essentially you use this formula. So this formula can be derived from the Taylor polynomial approximation of the function f. Okay. And now when you try to implement this formula in MATLAB or any computer language, then there will be some errors. So the errors will depend on h, yeah? And there's two sources of errors. So the first obvious source of errors is the truncation errors. The truncation errors is the remainder terms of the Taylor polynomials. And you see the truncation errors will be order OH square, right? So it comes from here. And then when you implement this formula, you always have a rounding errors. The rounding errors is when you store a number in a floating point system, yeah? And the rounding errors come from this expression. And because, all the terms here are real numbers, so it will incur the rounding errors of order epsilon. So remember, epsilon is the machine for epsilon is the gap between 1 and the next machine number, and it's about 2.2 10 to the minus 16. Okay, and because this expression divided by h squared, so the rounding errors is of order epsilon divided by h squared. Okay, and so the total errors will be of order OH squared for the truncation errors, and the rounding errors order epsilon over h squared. And you see that when h go to 0, then this term go to 0, but this term goes to infinity. So somewhere in between, when h go to 0, then this errors is minimized. And when this error is minimized, then we call it the step size h, we call it the optimal step size. Okay? And now the whole point of this question is you have to show that the optimal step size is about epsilon to the 1 over 4. So now we define the function EH to be the total errors. And it will be C1, some constant C1 h squared plus C2 epsilon over h squared. And so from calculus, we know that EH will obtain minimum or maximum when partial derivative or when derivative of E with respect to h equals 0. So you take dE over dH and you set it equals 0. Okay? So dE over dH is just 2C1H, and this one is just 2C2 epsilon over h cubed, and you set it equals 0. Okay? And then when you rewrite the equation, it will be C1H equals C2 epsilon over h cubed, and then you multiply h cubed. Here you got h4 C1 C2 epsilon, or h4 is C2 over C1 epsilon. Okay, so the last equation just show that h will be of order epsilon to the power 1 over 4. So strictly speaking, we want to show h, when h equals epsilon 1 over 4, then the errors is minimum. So we have to take the second derivative of E, and we show that this one is positive. And if you take the second derivative, of E with respect to h, then you got 2C1, and you got 2C2, well actually 6, yeah? 6C2 epsilon over h to the 4, and this one is a positive number. because C1 positive, C2 positive, epsilon positive, H positive. So therefore, E is minimized when H is equal H star is of some constant epsilon 1/4. Okay, so that's it.